So we're aiming for the question?
Number 10 on the gateway review.
10 on the gateway. Do you know what that is? That's our implicit differentiation. So do you remember what it is?
Find dy over dx of 3y squared plus x to the third y equals 30.
Is there a y in there? Equals 40. So we're going to do our magical implicit differentiation. So we're doing an annual derivative on y. It's an unknown function. So we go 2 times 3 is 6y to the first times the derivative of y, which we don't know, but we're going to call it y prime. Now, the x cubed y is a product rule derivative because you've got an x cubed times a y. So that's going to be the first x cubed times the derivative of y, which we'll call y prime, plus the second y times the derivative of x to the third, which is going to be 3x squared, and then the derivative of 40 is going to be 0. So 3x squared y, you okay with that? Now, the y prime terms stay on one side of the equal sign, the non-y prime terms go to the other side. So I'm just going to move that 3x squared y to the right side by subtracting it. And on the y prime side, you can factor out that y prime, and that's going to leave a 6y plus x cubed. And we can divide that all over to the other side. That'll be a negative 3x squared y all over 6y plus x cubed. And that's our derivative. Okay? You understand how the gateway thing is going to work? So you'll get 10 derivatives, kind of like what you see on that review. And you'll see trig derivatives, product rule, quotient rule, chain rule. If you do the derivative part correctly, you'll do fine. Each problem is worth 10 points, is a 100-point test. If you don't do a derivative right, remember the right derivative of the trig function, you incorrectly or don't recognize there's a product rule, quotient rule, or chain rule, it's a minus 10. You have to score 80% or better, or it's a 0, and then you can retake it as many times as you need until you can get the 80. So you just have to be good at doing derivatives. You just have to know those.
Is that test this week?
Yeah, I think it's Wednesday and Thursday. Does it say that on Canvas? I think it's so for you, or Thursday, Friday, I think. So I think for you guys it would be Friday.
Thursday.
Thursday. Yeah, so you guys would be Thursday. It won't take the whole period. So we'll do the gateway and then we'll go on and I'll still teach a lesson. So it's just 10 derivatives. So I'm not trying to put a time pressure. It's not like a chart quiz where I'm going to say, if you're not done here, I'm going to yank it. But you don't have unlimited time. You either know it or you don't. So, yes.
So are there going to be any inverse trig derivatives?
No, I didn't put any inverse trig function derivatives there. Perhaps I should have. But have we done an inverse trig derivative quiz yet?
Yeah.
We did, didn't we? Okay. There may be more of those coming too. Just can never have too many quizzes. Anything else? Next test is going to be a week from Friday. I got aced out in my usual 8 to 9:30 time slot. So it'll be 9:30 to 11. I know that makes you very sad that you get to sleep in on that day. But we're headed towards another one. Okay. But let's talk about then, we're going to talk about 3.9. Sometimes called the tangent line approximation. And it is also referred to as linearization. trying to expand your vocabulary here. So the tangent line approximation, or also referred to as linearization. So an important idea in calculus is the idea that differentiable functions are locally linear. So what that means is, pull out your calculator and let's graph y equals x squared, and we'll just go zoom 6, so we're all going to start with the standard 10 by 10 window. I'm going to try to show it on the video, but you can, if you're watching the video, you can do this with us and we'll talk about what that should look like. So, I'm going to pull up mine. So I'm going to go y equals, I'm going to clear that old stuff out, and I'm going to put in x squared, and I'm going to go zoom 6, and that's going to give us just a standard 10 by 10 window. So I don't know if you've ever played around with your calculator and zoomed in. So this is a pretty bendy function there, especially right at the vertex where it's y equals x squared. But it's differentiable, which means it doesn't have a corner or a cusp or a discontinuity. So the idea is if we zoom in enough, and it may be a really small section, it will look very much like a line. So that's what we're going to do. So if you go to the zoom button, right in the middle on the top row, drop into zoom in, and hit enter, and you'll see the cursor is at 0, 0. And we're still just looking at our original 10 by 10 screen. Hit enter, and we're going to zoom in. You can kind of see the tick marks where we've gone to kind of, it looks like we're about 2.5 by 2.5 now in each direction. And then hit enter again, and we'll zoom in more. And now you can see the parabola is starting to flatten out because we're getting closer and closer. It's like you're pushing your face up to that screen there. And you can see we don't even see a tick mark anymore. So our x min, x max, they're under 1 now. And I'm going to hit enter again, and it's almost flat there. And now let's do it one more time, and you can almost barely see it. It looks like it's just hugging the x-axis. So it's almost become that horizontal line. Remember, that's right where we're at the vertex there, where it's bent the most that it does bend. Now, you look at the window. If you hit the window, you can see, we're really up close and personal there, right? Our x min and x max are like about a negative 0.04 on either side. Okay, but the idea is, even with this very curvy function right here, if we zoom in enough and you look at a really small section there, it looks a lot like a straight line. And so the idea behind a locally linear function, that is a differential function being locally linear, is if we have reason to, it would be a reasonable thing to approximate the function itself with a straight line, as long as you don't go very far away from the point of tangency, because that's going to be the tangent line that we use to approximate it. The idea is that a tangent line is a reasonable approximation to the actual function itself if you don't go very far away from the point of tangency. Now, why we want to do that isn't totally clear, but we'll kind of come up with some examples of that in the next couple of days. But the idea behind it is that it should be a reasonable thing to do. Now, if we don't have a differentiable function, then that doesn't work. It's not locally linear. So let's go back to y equals, clear off our parabola, which was a nice differentiable function, and let's put in the absolute value of x, because that is not differentiable. It's got a corner point at x equals 0. So we can go to the math menu, and then right arrow to numerical, and then that very first one, ABS, is absolute value. So hit enter, and I'm going to put x in there, and there's our absolute value of x. Does anybody's look different than this? You have an older calculator, it's going to say the word ABS. You all okay? Okay, let's go back to zoom 6. We can go back to the 10 by 10 like we did before. So zoom 6, and there's our 10 by 10 window. And we can see it looks like an absolute. It's a little distorted because we should, our screen is rectangular rather than square. And so it's kind of distorting that. It should look like those are going up at 45-degree angles, but they're not. In fact, let's go back to zoom. And I think if we do number 5 square, it'll change the x-min and x-max so that the screen really looks square, and that looks more like it should. Okay, so now we have our 10 by 10. Well, it's not quite a 10 by 10 anymore. Now, let's do the zoom in again. So we go zoom down to option 2, zoom in, hit enter. It again puts the cursor at the origin. So we're going to zoom in. I'm telling you this because this can be hard to distinguish. Hit enter, and you can see there's the tick marks have become spaced out. So we're no longer going from -10 to 10, but the graph itself doesn't look much different. And if you hit enter again, and you can do this all day, and it's not going to change. So it is not locally linear at x equals 0 because it's not differentiable there. And so there is no way to get a good approximation to the absolute value of x at that corner point, trying to use some kind of tangent line or some kind of line, linear approximation. Okay, so that's all I wanted to do with that. I'm going to turn this off. Does that kind of make sense at least? I need nods of heads. So what the idea then is we're going to use a tangent line to approximate a curve. So we've done this, I mean, we've found tangent lines before. The big difference is now we're going to call them a linearization. So, so don't be confused by the symbolism that I'm going to use here and the new word that I'm going to call the linearization. So if f is differentiable at x equals a, then, so this is going to look weird, but we'll talk about it in a minute. Then L of x is equal to f of a plus f prime of a times x minus a is what we call the linearization. So here comes some words now. Linearization of f at a. Did I leave you out there the whole time? Ah, you guys, Taylor, you're supposed to notice that Abby's gone. I'm old and senile. I have an excuse. Sorry about that, Abby. We're talking about a tangent line approximation. I'm glad you came in and didn't sit out there the entire period. If f is differentiable at x equals a, then L of x equals f of a plus f prime of a times x minus a is the linearization of f at a. So we say f of x is approximately equal to L of x close to a. X equals a is also called, x equals a is the center of the linearization. It's called the center of the linearization. So this is a lot of new words and symbolism for an idea that we have been doing for quite a long time. That is, we're just talking about finding a tangent line to a curve. So all of this notation, let me just show you, that's really just the tangent line. So it's not really anything all that wild and crazy. So here's our function, f of x. It's differentiable, so there's no corner points, there's no cusps, there's no discontinuities. We pick a number a, so that's going to be our x equals a. And because it is on the curve, y equals f of x, that means its y coordinate must be f of a, exactly. And so that point right there is a comma f of a. And that's the point on the curve. Its tangent line to that function at that point has a slope that's going to be what? It's positive because this is rising, but more specifically, how do you find the slope of a tangent line? Take the derivative and evaluate it at that point. So the slope of that tangent line to this curve at that value of x would be f prime of a. Does that make sense? So the slope is f prime of a. Okay? So the tangent line in point slope form is going to be y minus f of a, good, is equal to f prime of a, because that's our slope, times x minus a, there's our point slope form. See it? I'm just going to add that f of a to the other side, and we have y equals f of a plus f prime of a times x minus a. Then, to try to obscure it a little bit more, I'm going to give this a new name. I'm going to say that is the linearization of x. And that's what we did right up here. It's just the tangent line. Okay? So the idea is, if we find the tangent line to occur at a particular point, and for whatever reason may be, and we'll talk about other reasons down the road, we want to find the value of the function a little bit away from where we found the tangent line. If we would like to know what's the value of the function over here a little bit, or over there a little bit, using the tangent line is a reasonable thing to do. That's going to give us a pretty decent approximation. And there's nothing easier to use than a linear function. You know, y equals mx plus b, that's about as simple as we can get in terms of functions. This might be something really crazy that may be hard to evaluate, but if we just want to get a good approximation and we don't want to go too far away from the point of tangency, it's a reasonable thing to use that tangent line. That's what we're saying. That's a linearization. So let's see what kind of questions we can ask. So find the linearization. Remember, that's just code for the tangent line. Of f of x equals the square root of 1 plus x at x equals 0. And use it meaning the linearization, to approximate the square root of 1.02. So if you'd like to know what the square root of 1.02 is, imagine we don't have a calculator, but being the astute calculus students that we are, we know that we can find the tangent line to this curve and use a tangent line to approximate this, and that should be fairly close. Okay, so to find the linearization, we need a tangent line, which means a point and a slope. What's the point going to be? What's the x value going to be? 0. So how do you find the y coordinate? Plug in that, right? So f of 0 is just 1. So that's nice. Not only do we get a point, it happens to be a y-intercept. That's even better. Now we need a slope. How do we find the slope? The derivative. So we need f prime of x. So this is a pretty mild chain rule derivative, right? We have 1 plus x to the 1/2 power. So we're going to take the 1/2 times 1 plus x to the good times the derivative of the inside function, which is 1. So I'm going to write this in a more user-friendly form, something that's easier to plug numbers in. I'm going to go 1 over. The 2 from the 1/2 is in the denominator. The negative 1/2 power moves it to the denominator, and the 1/2 is a square root. So there is our derivative, 1 over 2 square root of 1 plus x. And where are we going to evaluate this? At 0. And that's going to be our slope. And if we plug in 0, we're going to get 1. So our tangent line is going to be, well, we have slope and our point happen to be the y-intercept. So we can write it in slope-intercept form. It's going to be y equals 1/2 x plus 1. Now remember, we're going to evaluate, we're trying to approximate the square root of 1.02. This is a pretty easy way to do it, right? We're going to do all this just in our head. Now, here's the trickiest part. If we want to approximate the square root of 1.02, and our original function was square root of 1 plus x, what is the value of x we're going to plug in? What is it again? Yes, 0.02, not 1.02, right? So that's probably the trickiest part of the whole thing. Because we have square root of 1 plus x. To get 1.02, we just need the x to be 0.02. See it? So I'm going to go back to this crazy functional notation because it's easier to show I'm plugging in 0.02. So I say L of 0.02 is going to be 1/2 of 0.02 plus 1. Well, half of 0.02 is, and added to 1 is going to be 1.01. Kind of crazy? So, how good an approximation is it? Grab your calculator. So here's our approximation. You're saying that's approximately the square root of 1.02. On your calculator, when you plug in 1.02, tell me what you get. 0.00995. Not too bad, huh? That kind of cool? Now, granted, we didn't go very far away from the point of tangency, right? Our tangent was at 0, and we just plugged in x as 0.02. So we didn't go very far away, but still, it's kind of impressive for arithmetic we could just do in our head. You know, that's kind of neat. Now, it's not very good for very long. The further away you go, the worse it gets. But there you have it. Okay? So, I'm going to give you something that we're going to try to approximate. See if you can think what would be a good function to use and what is a good choice of x that'll take you close to where we want to approximate this, and then see if we can first find the linearization, and then can we use the linearization to approximate that value. Okay? Oh, this will be fun. Okay, so before I do that, let me talk a little bit, I neglected to mention this. How can we tell if our approximation is an overestimate and underestimate. Well, let's consider, now we saw, because we threw it on our calculator, so we saw that ours was going to be an overestimate. Without that, let's just imagine, we know what the original function was square root of 1 plus x. We know what that looks like. Right? We know the square root of x function. X plus 1 is going to translate it 1 to the left. So it's going to look something like this. Okay? We found the tangent line at x equals 0. So here is what our tangent line looks like. Now, what we did was use the tangent line to approximate the value of the curve. So we were using a value of y coming from the pink tangent line to approximate the purple function. So since we went over here, 0.02 to the right, is our approximation going to be an overestimate or an underestimate? Overestimate, why? Because what? So talk to me in calculus language here. We know that the tangent line was going to provide an overestimate to the value of the function, no matter which way we went, right? Whether I put in a value of x bigger than 0 or one that was smaller than 0, it was going to be an overestimate. So this was what was happening. Why? Because the function is concave down. Okay, so you refer back to the concavity. If we had had a function that was concave up, and we had our tangent line to that curve, and we wanted to go a little ways away either direction and use the tangent line as an approximation to the value of the function, because the function is concave up, this would have been an underestimate. So this is going to be important. I would just draw the picture, but this is a commonly asked AP Chem question. Is it going to be an overestimate or underestimate, and why? And so your justification has to use the language of calculus. So yes, it's going to be an overestimate, but don't say because look at the picture. Say because the function is concave down. Okay. Good. All right. So let's use a linearization. So use a linearization to approximate the square root of 123. We up for doing this at the board or no? Is that too big a leap? No, we're not. It's okay. We'll do it together. So I'm giving you very little to go on here, except I just want a linearization. So what you have to think is, a linearization means we're going to use a tangent line. In order for you to find an equation of a tangent line, you first got to think of what function are we talking about? What is the underlying function here that we're trying to approximate? The square root of x, exactly. See it? Because we're trying to find the square root of 123, that function that is not been explicitly mentioned is the square root function. Now, we also then, we're going to find a tangent line to approximate this. We want to find an equation of a tangent that is close to what we're going to approximate here. Don't choose, and you want to also choose a number that is easy to compute, that you're going to be able to do this without the aid of a calculator, because you won't be able to use a calculator on this. So you're thinking, what is a nice number close to 123 that you can evaluate in the square root function without using a calculator? I'm going to use the perfect square. 121 is the closest perfect square. Does that make sense? That's 11 squared. And 12 squared is 144. So we're going to choose x to be 11. Okay. I'm going to give you a moment to see if you can do that. So we're trying to find a linearization. That means you are trying to find an equation of a tangent line. 2f of x equals square root of x at x equals 11. At x equals 121. Sorry. That sound better? Okay. Once you come up with a tangent line, then you're going to plug in what you need to evaluate that. I'm sorry, x is not 11, x is 121. That's what Priya was trying to tell me and I wasn't hearing her. I got my tangent line, so I don't want to take all the fun away, but when you get to your tangent line, you can compare, see if we agree up here. Okay? You don't have to say it just to make me feel better. What are we going to plug in for x? 123. Does that make sense? And solve for the y. I'm going to add this 11 to the other side. And we're going to plug in our 123. So 123 minus 121 is 2. And if you believe in canceling, and who doesn't believe in canceling, you can say this is 11 and 1/11. That's good. Okay? Now, if you're dying to know, you can throw this on your calculator and compare it to the square root of 123 and see how well we did. If you don't care, you don't have to. You're just confident. Ainsley, what'd you get for square root of 123?
11.0905.
And did you go 11 plus 1, 11?
Yeah, it's 11.0909.
Oh, not too bad, huh? Okay. All right, well, let's play the same game, and we'll change it to cube root of 123. Now we can come to the board because we have no excuses. So I'm going to pause it here. We're going to answers up here if you need to check your work. But need help on getting to that?